Have you ever seen this toy? Yaps, in Indonesia we call it the lato-lato game.
Lato-lato games are very viral in Indonesia, from children to adults, and even have competitions. The popularity of lato-lato has led many people to parody it by replacing baseball with basketball, volleyballs, and even LPG gas.
I have two lato-lato. This is the first lato-lato. And this is the second lato-lato. Why is this first lato-lato movement faster than the second lato-lato? Let's find the answer in this video.
Audio Jungle. Audio Jungle.
Hello, my name is Tazkia Wardah from Said Ali Rahmatullah State Islamic University. In this video, I will explain about my science project for Final International Walisongo Science Competition.
The tools and materials in this experiment are first a pile of balls of the same mass and size. The second is a rope. Third is hooks or handles are optional. How to make it? Prepare the rope, then insert the hook in the middle of the rope. Then insert the first ball that has been hooked with the rope. Do the same for the second ball. Then tie the rope like that so that the length of the rope remains the same. First, the two balls are hung on one side. The system will move if given an external force. Then there will be a collision between the two balls. Then the force on the two balls are as follows. So, in 3 dimensions, x, y, z, and we have x1, x2, y1, y2, z1, z2. The two pendulums remain in the xy plane, so the z component does not change. Then I will write z1 equals 0, z2 also equals 0. We have got two constraints, then we find another constraint. M1, its point x1 and y1. We'll always lay on a circle because it's the fixed distance from a certain point, so we can write down the equation of a circle. L square equals x1 square plus y1 square. And then for M2, its position x2 and y2, so we can write down the equation of a circle. L square equals x2 square plus y2 square. So there are 4 equations of constraint.
There are generally 2 types of constraints: holonomic and non-holonomic constraints. Holonomic is don't limit the range of motion of object, and non-holonomic is limit the space for object to move. These two pendulums are included in the holonomic constraints because they can move freely at theta 1 and theta 2.
S is degree of freedom equals 3 for 3 dimensions. Because in general things can move in 3 dimensions, so we can write down. And N is particles we are looking at there. Here there are 2 masses, so we can write. We can subtract our number of constraint equations. M is number of constraints, so we should have 2 degree of freedom. So we only need to generalized coordinate. So theta 1 and theta 2 is our generalized coordinate.
The degrees of freedom of these two pendulums are theta 1 and theta 2, meaning that objects are free to move at theta 1 and theta 2.
To find the equation in the system, we can use the Euler-Lagrange equation. The Euler-Lagrange equation is generally shown by equation 1. To determine the Lagrangian of the system, the kinetic component indicates by T and the kinetic energy component indicates by V. The statement shown by equation 2. two pendulums that is divided by small angle theta 1 and theta 2. We analyze using the Lagrangian in the second equation. For T, use the rotational kinetic energy, which is half of the inertia omega squared. Omega is the angular velocity, none other than theta dot, which is the derivative of angular position against time then squared. Then we get T is half ml squared theta dot 1 squared plus half ml squared theta dot 2 squared, which is shown in equation 3. Then we find the potential energy is mg minus L cos theta 1, negative because the reference point used is this. Then plus mg minus L cos theta 2. Then we will get equation 4. We can substitute this equation 3 and 4 into equation 2 and get L in equation 5. The Lagrange equation for this system are shown in equation 6 and 7. To get the equation of the first pendulum system, the mathematical solution is shown in equation 8. To get the equation of the second pendulum system, the mathematical solution is shown in equation 9. So, the equation of motion for these two pendulum systems are shown in equation 10 and 11. If we see that the equation of motion are none other than oscillation equations, G per L is none other than omega squared, meaning that omega is equal to the square root of G divided L. Because omega is 2p per T, then the T is 2p the square root of L divided by G.
So, from the equation that we have found, namely the period equation,
the period of motion is directly proportional of the square root of the rope length, which means that the longer of the rope, the slower the movement. The shorter the rope, the faster the movement.
physics is fun and easy, right?